All right, let's dive right into a fascinating scientific detective story where the search for alien life took a massive, entirely unexpected turn. Today, we're exploring this brilliant piece of recent astronomical research that, honestly, just reminds us exactly how tricky the universe can be. We're going to look at how the hunt for one of the most famous theoretical alien megastructures out there accidentally led scientists right into the path of some of the most extreme, intensely dust-obscured galaxies in the entire cosmos. It's an amazing story about incredible technology, incredibly careful data analysis, and, well, cosmic photobombers. So this is the provocative question at the heart of our explainer today, and it's a concept that actually dates back over 60 years. Back in 1960, the physicist Freeman Dyson proposed this wild but highly logical scenario. He theorized that as an extraterrestrial civilization advances technologically, their constant, ever-growing demand for energy would inevitably force them to look to their host star. To put that into perspective for a second, humanity currently uses roughly 20 terawatts of power. If an advanced civilization could somehow capture just 1% of their sun's power, it would exceed our entire global energy needs by a factor of over 100 billion. No way they pass that up, right? And the structure they build to capture that colossal energy is what we now call a Dyson sphere. So we're essentially talking about the ultimate solar panel, which would theoretically produce a very specific mid-infrared waste heat signature that we could actually detect all the way from Earth. Now, contrary to what you see in a lot of popular science fiction, a solid, monolithic shell completely enclosing a star is highly impractical. It would literally just buckle under its own gravitational forces. Instead, scientists envision more of a swarm of independent stellar orbiters or panels. But, regardless of its exact shape, the laws of thermodynamics dictate a very specific outcome. Converting all that stellar energy would inevitably produce high-entropy waste heat. This means a Dyson sphere would cause its star to look unusually dim in regular optical light, but incredibly bright with a huge excess in the mid-infrared spectrum. And with that exact signature in mind, the hunt was on. Armed with this theoretical signature, a team known as Project Hephaistos went looking. Out of 5 million stars analyzed in a massive survey, Project Hephaistos found exactly 7. 7 perfect candidates that matched this precise theoretical signature. These were M-dwarf stars that displayed this bizarre, totally unexplained mid-infrared excess. And what made this discovery so thrilling at the time was that no well-known astronomical phenomenon could easily explain it away. I mean, they looked at extreme debris disks, but they just didn't match the known types. For a brief, shining moment, it really looked like we might have actually found something truly anomalous hiding right in our own galactic backyard. But, well, here is the plot twist. As brilliantly as these candidates fit the profile, independent researchers started suspecting we were actually looking at background contamination. Shortly after the initial discovery, other astronomers started looking really closely at these 7 candidates. They found radio sources associated with a few of them and hypothesized that actually the infrared excess wasn't coming from an alien megastructure around the star at all, but rather from an incredibly bright, extremely distant galaxy sitting in the exact same line of sight. Essentially, these local stars were being perfectly photobombed by a rare class of galaxy known, rather amusingly, as a hot dog. Now, what's really interesting about these prime suspects is just their sheer, staggering scale. These are galaxies that take cosmic extremes to the absolute limit. Hot dogs, which stands for hot dust-obscured galaxies, are exceptionally rare. We're talking only about 1 found per 31 square degrees of the sky. Their gas densities are completely off the charts, so high that the gas is what we call Compton thick. This literally means photons traveling toward us are constantly crashing into electrons and losing energy along the way. But despite being so intensely obscured, they boast a colossal infrared luminosity, making them some of the brightest known galaxies in the universe. Oh, and their stellar masses? They are the absolute heavyweights of their respective cosmic eras. If you could somehow see one of these intense, dust-obscured monsters up close, like this rendition of the turbulent hot dog W2246-0526, you just see pure chaos. The immense power driving these galaxies comes from a supermassive black hole actively feeding at their absolute center, an active galactic nucleus, or AGN. This AGN is so luminous that it completely dominates the mid-infrared light, even though it's buried under a literal mountain of dust. The radiation pressure from this black hole is so intense, it actually blows away the surrounding gas, creating massive outflows that eventually completely shut down the galaxy's ability to form any new stars. So, how do these fit into the bigger cosmic picture? Hot dogs actually represent a very specific, extremely buried phase in massive galaxy evolution, which is usually triggered by violent mergers. Standard spiral galaxies undergo this hierarchical growth, collided and merging over time. These violent mergers create massive inflows of gas, sparking intense periods of star formation that we call starbursts. And as the supermassive black hole grows and gobbles up this material, the AGN becomes deeply, deeply buried in dust. Hot dogs represent that exact phase. Eventually, those massive outflows we just talked about blow all the dust away, revealing a brilliant, unobscured quasar before the whole galaxy finally settles down into a quiet, quiescent state. To actually crack this case and see what was really hiding behind candidates D and E from the Hephaistos list, researchers needed the big guns. So they secured time on the ultimate forensics lab, the James Webb Space Telescope. Now, preliminary analysis of these two candidates showed their infrared spectra were significantly redshifted, which basically proved they were indeed extragalactic objects sitting way, way behind the foreground stars. But to definitively prove these photobombers were actually hot dogs, the researchers needed to deeply analyze the specific type of light they were emitting. And that required the totally unparalleled sensitivity of the JWST. To pull the spectra, which is essentially reading the chemical DNA of the light coming from the exact coordinates of these strange stars, they relied on the MIRS, an integral field spectrometer. What makes this instrument such a game changer is that it doesn't just take a flat 2D picture. It actually combines imaging and spectroscopy in a single exposure. It literally slices up the field of view, generating a separate spectrum for every single slice, and then reconstructs all of that into a three-dimensional data cube. This lets astronomers see exactly how much light is being emitted at every single mid-infrared wavelength, giving them the raw data they need to identify the exact physical makeup of those distant galaxies. Because when you look at the shape of the continuum and the specific peaks and valleys of a galaxy spectrum, it's like reading a barcode. Scientists can read its exact physical properties. The smooth, underlying curve that you see there is the continuum, which tells us about the overall temperature and energy distribution of things like gas, stars, and dust. Superimposed right on top of that continuum are sharp peaks. These are emission lines indicating excited, radiating gas. And then you have dips, which are absorption bands, where cold gas and dust right in the line of sight have actually swallowed up specific wavelengths of light. So the crucial point for our researchers was comparing two highly specific features found in the mid-infrared: PAH emission and silicate absorption. PAHs, or polycyclic aromatic hydrocarbons, are these large molecules formed in the harsh winds of dying stars. When they absorb starlight, they heat up and emit mid-infrared light. So, strong PAH features basically mean the galaxy is dominated by rapid star formation. On the other hand, a deep absorption dip at exactly 9.8 microns tells you there is amorphous silicate dust present. A strong silicate absorption means there is a thick, thick layer of cold dust deeply obscuring a massive black hole. The researchers then used a very specialized diagnostic tool to finally classify the true nature of these photobombing galaxies. See, because powerful active galactic nuclei can actually destroy PAH molecules with their intense radiation. Comparing the strength of the surviving PAHs against the depth of the silicate dust absorption tells you exactly what kind of galaxy you're dealing with. They plot this on something called the spoon diagram. And yes, astronomers really do love naming highly complex astrophysical diagnostics after kitchen utensils. This diagram divides galaxies into 9 distinct classes. On one end, you have spectra dominated by starbursts. On the other, spectra completely dominated by deeply obscured nuclei, which is the exact signature of a hot dog. And here is the final verdict. The background galaxy behind candidate D perfectly matched the profile of a hot dog. It had a steeply rising continuum indicating warm dust, moderate silicate absorption, and very weak PAH features, meaning the black hole was totally dominating the emission. But the galaxy photobombing candidate E showed a pretty different profile. It had a shallower slope, weak silicate absorption, and strong PAH features. So this actually placed candidate E into a completely different category called a bump dog, which is a galaxy heavily obscured by dust, sure, but primarily powered by intense starburst activity rather than a supermassive black hole. Now, you might be thinking, well, that's a bummer, no aliens. But honestly, This isn't just some debunked mystery, it's an absolutely massive win for the scientific method. It teaches us exactly how to refine our search for actual extraterrestrial intelligence. By meticulously analyzing this JWST data, scientists conclusively proved that these Dyson Sphere candidates were just incredibly rare galactic coincidences. Far from being a failure, this research arms future SETI projects with crucial knowledge. When we look for the subtle waste heat of an alien megastructure in the future, we now know exactly how to identify and filter out the intense glare of these ultraluminous, dust-obscured background galaxies. Let me leave you with this final thought as we wrap up this explainer. Every single time we look deeper into the universe, the mysteries only get bigger. While we definitely didn't find a Dyson sphere this time, we did peer billions of light years across the universe to uncover galaxies operating at the absolute extreme edges of physics that just happen to perfectly align with stars in our own galaxy just to trick our telescopes. It really makes you wonder, as our instruments get sharper and sharper, what other brilliant cosmic illusions are perfectly lined up out there, just waiting to be unraveled? Thanks for exploring this with us, and keep your eyes on the stars.